Elementary statistics, looking at section 11.3 contingency tables. So when we take a look at a contingency table, they're also referred to as a two-way frequency table. It's a table consisting of frequency counts of categorical data corresponding to two different variables. One variable is usually categorized rows, and the second variable is categorized by the columns. So for instance, they talk about, just right down here, we talk about the study of success with different treatments for stress fractures. So we talk about like a broken bone. Surgery, there was 54 successes, 12 failures. So there'd be a total of 66 surgeries being done here. Then we talk about weight-bearing cast, 41 to 41 to 51. Non-weight-bearing cast for 6 weeks. So basically, we're starting to compare basically columns, these columns with the success failures to different categories as we start going into the problems. And we start seeing if there's some sort of relationship between them, that these are in relationship to what's happening over here, or if it's not. So, the test of independence. The test of independence. So we test the null hypothesis, that is a contingency table. The row and column variables are independent. That is, there is no dependency between the row variable and the column. So that means there's no relationship between what happens in those rows and what's happening in the columns. So what we do is we look at, once again, our observed frequencies, expected frequencies. R is the number of rows, C is the number of columns. And once again, do not include the labels in here. It's just the data that we're following. If we consider what's going on here, once again, sample data are randomly selected. The sample data represents as frequency counts in a two-way tables, and then the expected frequency E is at least 5. So we have to expect that there's at least 5 in each of these categories, otherwise there's not enough data really going into this. So, your null hypothesis. Your null hypothesis is always going to be stated that the row and column variables are independent of each other, that they have no relationship, that there is no way that they're going to be influencing each other's. The alternative hypothesis is going to be that they're dependent. Once again, we're going to run a chi-squared test where the chi-squared, our test value, is going to be the summation of observed minus expected squared divided by expecteds. Once again, the expected is going to be the row total times the column total divided by the grand total. And this is how we find that expected value in here. Degrees of freedom are a little bit different on here. We're going to take the number of rows minus 1 times the number of columns minus 1. So if we have a 2 by 3, that means we would take 1 times 2. That would be our degrees of freedom. Once again, this is a right-tailed test. Now, there are some calculator operations we'll be doing on here, and there is a very specific test that we actually will be able to apply, but it will be quite a bit of work to actually go through this. So I'm going to tell you, you're going to want to write down our flow chart, because basically kind of like it lines out in here, we're going to have to define a matrice. So we're actually going to have to not just be able to type in our matrice, we're going to have to define what our matrice is, and then we'll be able to go through our chi-squared test. Okay, so we'll be actually implementing a chi-squared test on here for the matrice relationship of contingency tables. Continuing on, they kind of have, once again, their flow chart. We talk about compare the observed values with corresponding expected values. If they're close, if they're far apart, once again, we start looking at fail to reject. Reject independence. So it kind of depends upon what we're talking about. Now, expanding this just a little bit, we don't do too much with this, but just so you have some notation and some other things that do go into this. We talk about the test for homogeneity. In the chi-square test of homogeneity, we have samples randomly selected from different populations. and we want to determine whether those populations have the same proportions of some characteristic being considered. Okay, so is a test of a claim that different populations have the same proportions of some characteristics. This could be comparing different ethnic races on different diseases, whether they come down into it or not, to whether it's a gender or an ethnic related disease, or if it is an overall disease that could influence anybody. Kind of like now with our coronavirus or COVID-19, we have no specified characteristic for a different population that's affecting everybody equally. It's not just attacking certain ones, but they are seeing signs that in the African American race it is hitting a little bit harder, but they can't tell if that's because of other, wouldn't say ethnic issues, but more of a cultural or social economic issues that could be influencing that also. We also can talk about the Fisher exact test. So one other one is a Fisher exact test. It's often used for a 2x2 contingency table with one or more expected frequencies that are below 5. Okay, so once again, if we have our frequencies where they're below 5, well, we got to go into maybe some different testing in here. There's also McMahon's test for matched pairs. Once again, we talk about treatments, whether they're curing or not curing within here is kind of where this is going. So there's other tests that do apply to these contingency tables, so don't get me wrong and say this is the only one we're going to be doing. Well, in the class, this is the only one we're going to do. If you're going more advanced, there might be one a little bit more specific to what you need, but do realize that we'll just be using the basic of the test itself.